So a binomial distribution is a way to theoretically calculate a probability when we repeat an event over and over again. We repeat an experiment over and over again with the same probability of success each time. So a great example of this is this Galton board. Here's a little easier to see picture of what's going on here. We drop something like a marble or token like Plinko in Price is Right. You drop that in and it's a 50-50 chance of going left or right, and then it kind of keeps bouncing down as it goes. So one example is it could actually go left every time, and it's pretty rare. You see, we don't really, in this picture, we don't have any results over there, but that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 to the left, and I would land over there. Now that's actually just as likely as any other combination. It's just that to land in the middle, there's a lot of different ways you could get there. So you could go left 5 times and right 6 times, or right 6 times and left 5 times. And so there's a lot of different ways you could land in that middle. I think for my example, I'm going to use just 10 levels because it's a nicer round number. If we go back here, I think they're using like more than 20. And so you get this very smoothed out, looks like a normal distribution. And that's what we're going to use this for a lot, is an approximation to a normal distribution. However, it's great because we're starting with a qualitative problem, just left or right. And eventually, when we're done, we'll have a quantitative probability distribution. So let's take a look at, I'm setting up a Google Sheets to kind of arrange this problem. We're going to have, in this problem, we're going to have 10 of those levels, 10 times where it can go left or right, each of them 50-50. So I'm going to start with all 10 go left. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 L's. For my simple event, only one way it can happen. And I'm going to call left success, so I'm going to have 10 successes and 0 failures. 10 L's and 0 R's is how you could call that. So I'll just add those in. And these success and failure is pretty arbitrary. The key is we have 2 outcomes that we group these into. So in other situations, we might have to kind of conglomerate multiple outcomes into one. For example, if you roll a 6-sided die, you could say rolling a 1 is a success, rolling anything else is a failure, and you could look at a problem like that. So here's my first situation. It's not going to happen very often. What we could do is calculate the probability of this by sort of putting together the pieces. And the 3 pieces that we have, just to scroll down here to the formula, is this nx. This is called n choose x. It's a combination function. You can use Desmos to do that, or your calculator. You can do it by hand using the factorial, but I'll show you a couple ways to do that. Then you have the probability of success with x successes as your exponent. That's using the multiplication rule. You just keep multiplying that same probability, and then probability of failures over here. Now with r's being 50-50, p and 1 minus p are both 0.5, and so all of these actually add together to just be 0.5 to the 10th power. So everything is really going to come down to this front piece here. So let me show you what I mean. That front piece counts how many ways it can happen. With our all to the left, we have 10 successes. We basically only have one way that can happen, times 0.5 to the 10. That's all 10 successes, times 0.5 to the 10 minus 0, which, first one is 10 successes, and it's n minus x, so 10 minus 10 is 0. So there's my first probability. That's how I could do that using Desmos. And in front, I could change this to NCR and basically say we have 10 trials, all 10 are successes. That's the same as that 1 up there. And I could copy that in here. So now let's look at the probability when we just have the 1 R among all 10. So we have 9 left and 1 right. So there's actually 10 different ways that this can happen. The way you could check that is use this NCR function and basically say we're going to have 10 trials and 9 of them are going to be successes there's that 10 different ways it can happen. And it's really just, where is the R? Is the R first? Is the R second? Is it third? And so on. So I'll type the rest of these. So there's my 10 different ways it could happen. So just going back to the beginning, where we see this picture, we're saying, it's going left 9 times, it's going right once. So it could go, right, then all left. It could go 1 and over. It could go so you can kind of see how we're mostly going left. We're going right once. So we're sort of like landing in the second from the left column because we're mostly going left and going right once. It's just we're not sure where that right's going to happen. So it's just giving us basically the same probability of each. So this is 0.5 to the 9th power and 0.5 to the 1st power. Essentially 9 successes and 1 failure. Still adds up to 10 trials. Since all of these are 0.5s, we're just shifting around the exponent a little bit. And we can do kind of a check here. There was my initial probability. If I swap this and make it, or shift this and make it a 9 and a 1, it's still the same probability, and it's just because that base is 0.5, so we're really just looking at 0.5 to the 10. But this time, we have 10 different ways it can happen in front, so our probability when we multiply it is actually 10 times bigger. Instead of being a 9.77 times 10 to the negative 4th, it's 9.77 times 10 to the negative 3rd, which it's just showing in a different notation there. So I can kind of continue this process for 8 L's. So that'd be let's see, let's make sure these match. I know I just said that it's all the same. It doesn't matter too much, but I like just to make this notation make sense here. So we'll see that as this second number slowly falls, this power slowly falls, and this last one goes up. So these two exponents always add to 10. We have a 10 there, and that's our number of successes right there. So we just keep continuing this on, and we see that this probability is going to get bigger and bigger as we continue this process. And there's 7 successes, right? So now we're up to about a 12% chance. And the reason why is because of that number in front. So let's dial it back and let's see how many ways it can happen. There's 45 ways that I can go left 10 times and right 2 times. There's 120 ways I can go left 7 times and right 3 times. So that's really the key is when we go back here, we see there's a whole bunch of ways to land in the middle. That's like 5 lefts and 5 R's. They could all happen at once. It could bounce around in the middle. There's a lot of paths that lead me to that middle, not as many to the outer edges. Now the real nice way to do this is with Staplet. You can go to binomial distributions, plug in your 10 for n and your 0.5 for p, and just get a quick visual of it. You can click on probabilities and see, 5 and 5 is most likely. We see how that really matches up with what we have here. And then we can calculate pooled probabilities like less than 3 lefts, or at least 5, and you get that probability notation and your answer and your picture and everything. So that's really nice. And then just to kind of look at another example that I think is a little more useful is, let's say you have right out of the homework, problem like number 15, we have a trial repeated 5 times with a 0.653 probability of success. We can plug that in and visualize the distribution, and then clicking on each of these or hovering over each of these, find a probability for each. If we need more accuracy or precision than that, we can adjust our rounding preferences at the bottom. If that's not enough, there is a way to do this in Google Sheets. What I like to do is set up my x and p of x columns. Start by putting in from 0 to n. And I'm still looking at this same problem. This is n equals 5, 0.653 probability of success, and I can use the binom dist function. Binom.dist. Number of successes will be in A2. Number of trials in this case is 5. Probability of success was 0.653. And then cumulative I set to false. So that's saying I don't want it to add up previous probabilities. I want to just find the probability in this row. Gives me a preview and then an autofill option. If you don't take the autofill option or accidentally miss it, you can go and just select that and fill down with that bottom right corner by dragging it. And then other things I might do is maybe adjust the rounding to the number of decimal places I want. So that one is 6 decimal points. It gives me a little more accuracy, a little more precision than I would get in Staplet. So check out my other video. I talk about using Staplet to graph, and I also talk about Desmos there. And then lastly, I give you an example that I think is really helpful to understand this, looking at an airplane and why they overbook the seats on the airplane.